TEKS 9B and 9D, exponential graphs and their attributes. So this is the practice to the notes that you did yesterday. So what I'm going to do is I am going to number each of these for you. I'm going to tell you to work on number 1. And then after you work on it, I'm going to give you the answer. So just like how the Ed puzzle worked yesterday. There is one quick note that I want to add, and it's a note that you guys did see on the Ed puzzle the other day, is that I did make a mistake. So when we're talking about exponential growth and exponential decay, let me write that off to the side. So growth and decay, I wrote when b is greater than or when b is less than 0. It's actually 1. That's my mistake. So for growth, b is greater than 1, and for decay, b is less than 1. So just keep that in mind. It's not going to apply so much to this practice worksheet, but when I post tomorrow's Ed puzzle and we're going over what it looks like in equation form, you'll see why that matters. Okay, so let's look at number 1. So this is number 1 right here. Let me label them real quick. So this is going to be number 2. And then down here, number 3, since they don't have numbers, and then number 4. So number 1 is a exponential graph showing particle ratio versus time. So particle ratio is the y-axis, and time, which is in years, is the x-axis. So the first question here says, is it a growth or a decay? So remember, if it's a growth, our graph, if we read it from left to right, is going up. And if it's a decay, if we read it from left to right, it's going down. So if I look at this from left to right, it looks like our graph is going down. So this is a decay. Okay. Then it says, what is the y-intercept, or in other words, the starting value? So remember, the y-intercept is where it crosses the y-axis. So let me write this over here. Quick note, crosses the y-axis. And remember, I said that particle ratio is the y-axis, so this whole thing is the y-axis. So we notice that our blue line, our blue curve, crosses the y-axis up here at 1. So that means our y-intercept, or our starting value, is 1. But if we look at the units, it says particle ratio. So the particle ratio equals, oops, I spelled that wrong, equals 1. Okay. Then it says, what is the asymptote? Remember, in Algebra 1, the only asymptote we are ever going to deal with is when y is equal to 0. Y is equal to 0. And remember, the line y is equal to 0 is the x-axis. So our blue line, that blue exponential function, is never going to go past the x-axis. So that's why our asymptote is y equals 0. Okay? Then it says, after 10,000 years, what is the particle ratio? So we need to find the 10,000 year mark. So the 10,000 year mark is right here. I'm going to actually change my color real quick. Is right here. And then I'm going to follow that line all the way up here. And then I'm going to see where it matches up on our y-axis. So it looks like it's going by, let's just put a guesstimate out there. So we know that this 1/4 here is 0.25 and this 1/2 here is 0.5. So it's a little above 0.25. So I would say maybe 0.3, which is 1/3. So that's what I'm going to say. I'm going to say after 10,000 years, what is the ratio particle? So the particle ratio is 1/3. 1/3. However, if you put anything between 1/4 and 1/2, then that would be correct. Anything in between these two, since it didn't give us an exact number. Okay? Last one says when the particle ratio is 1/8, how many years have passed? So 1/8, which is right here, notice it gives it to us already. So this 1/8. And it says about how many years have passed. So if we bring this down here, it looks like it's about, I think this is going by 1,000. Let's see, 16, 17, 18, 19. Yeah. So this is about 17,000 years. So 17,000 years. Okay. So if you put anything around there, then that would be correct. Okay, let's look at number 2. See if I can zoom in. Yep. So number 2 is talking about population size versus the generation. So let's see what it says first. So first it says, is it a growth or a decay? Growth or decay? Remember growth, if we read it from left to right, the graph is going up. And decay, if we read it from left to right, the graph is going down. So if we look at this from left to right, starting over here at 0 on the x's and going all the way to 10, if we follow that blue line, we notice it's going up. So this is a growth. Then it says, what is the y-intercept, or the starting value? So notice that our blue line doesn't go all the way to the y-axis, so I'm just going to assume it does. So I'm continuing it out here. And then it looks like that starting value is going to be exactly at 0. And remember, our y-axis is population size. So that means at the very beginning, our starting value, we had 0 people. So our population equals 0. Okay. Then it says, what is the asymptote? So again, this is going to be the same for every single problem in Algebra 1. Our asymptote is always going to be y equals 0. Okay? Then it says, after the 9th generation, how many people are there? After the 9th generation. So I'm going to find 9 right here. I think these tick marks are in between the numbers. So 9 is like right here. Then I'm going to follow that all the way up. Looks like it has about a point there. Then I'm going to follow this point all the way to the y-axis. So it looks like it's in between 20,000 and 30,000, so about 25,000. So after 9 generations, the population is equal to 25,000, or there's 25,000 people after the 9th generation. Okay, last question says, about how many generations will it take to reach 60,000 people? Okay, so 60,000 is all the way at the top right here. You guys notice it all the way at the top of the y-axis. So if I follow this all the way across, I notice that it doesn't cross my blue line. So I'm going to have to make a educated guess. So I'm going to draw this line up. Let me change the color so you can see that this is a blue line. Draw this blue line up a little bit. And then we're going to notice that it's going to cross about right here. So if I estimate that down, it looks like it's around 10 or 10.5 generations. So in between those two numbers. So I'm going to say about, we'll just say about 10 generations. 10 generations. But your answer could be anything between 10 and 11 generations, and that would be correct since it's kind of in between. Okay, let's look at number 3. Number 3. So let's see. It first says, is it a growth or a decay? So again, we're looking from left to right. So let me draw my arrow, left to right. Remember, if it's a growth, it's going up. That blue line is going up. Or if it's a decay, it's going down. So if we look at it from left to right, we notice that this blue line is going up. So it's a growth. Get that away. Okay. Then it says, what is the y-intercept or the starting value? So we're going to look at the y-axis over here, which is again talking about population size. And it looks like our blue line again starts at a 0 population. So our y-intercept or our starting value is at a 0 population. So it's where the population is equal to 0. Then it says, what is the asymptote? Again, the asymptote in Algebra 1 is always going to be y equals 0 since none of our graphs is going past the x-axis. Then it says, after 5 generations, how many people are in the population? So here's the 5 on the generations part on the x-axis. We're going to match it up with this blue line. So it looks like it's kind of in between 0 and 500. So that's going to be about 250. So the population is going to equal 250. Population is going to equal 250. Again, if you put anything between 0 and 500, leaning closer to 250, that would be correct. How many generations did it take for the population to be 3,500? So I'm going to find 3,500, which is all the way at the top here on my y-axis. I'm going to follow it all the way until I hit my blue curve. And then I'm going to follow it all the way down to see what generation it is. And I notice that the generation is at generation 10. So the population will be 3,500 when we reach 10 generations. 10 generations. Okay, last question, number 4. Okay, this is an exponential function comparing radioactive material in grams versus time in years. So again, our first question is talking about if it's a growth or a decay. So remember, if we're reading it from left to right, a growth is going to go up and a decay is going to go down. So from left to right, we notice this black line is slowly going down. So this is a decay. Then it says, what is the y-intercept or the starting value? So I'm going to look over here on my y-axis. I'm going to see where the point crosses that y-axis. And it crosses it all the way up here at 100. So our starting value is 100 grams of radioactive material. So at 0 years, it starts at 100 grams. What is the asymptote? Remember, the asymptote is always y equals 0. At the 50-year mark, how much radioactive material decayed? At the 50-year mark, so that's right here, how much radioactive material decayed? So it looks like at the 50-year mark, instead of 100 at the beginning, now it dropped all the way to 25. So after 50 years, the material is going to be 25 grams. 25 grams. And then last question, it says, how many years did it take the radioactive material to decay halfway? Or in other words, what is the half-life? What is the half-life? So if we started at 100 and we need to get all the way down to 0, halfway from 100 to 0 would be 50. Right here. So at how many years or how long would it take our material to decay to 50? So if we follow this to the graph and we look down at the x-axis, we notice that it would take 25 years. So after 25 years, our radioactive material would decay halfway. So the half-life is 25 years for this radioactive material.